So mechanical power. Mechanical power, I think, is a summary variable, so that the idea is to tell you if there is something wrong with the mechanical power, or the mechanical power exceed some values, you will have a problem with the patient, with the possibility of ventilator-induced lung injury. Remember, when you do ventilation, we do not cure the disease. We just maintain the patient's life until the antibiotics or the therapy of the basic disease is solved. So the only real goal of the mechanical ventilation is to maintain the life, that means adequate gas exchange without damage. Mechanical power just tell you if the damage is probable or not. Now, let's see, we have concentrated over years over the single breath. So we are looking at the tidal volume, the driving pressure, the flow, the PEEP. We forget the respiratory rate, because to damage something, we need energy. Energy, what is? Is the product of the pressure and with the volume. This is the amount of energy that we put in the respiratory system. Or we can put in the respiratory system this energy at every single breath. But of course, if I do 4 times per minute or 20 times per minute, is a completely different. And mechanical power is a comprehensive variable which includes tidal volume, delta pressure, flow, PEEP, and respiratory rate. Okay? So the VILI story is quite long, and we start immediately in the 70s. We started to recognize the barotrauma. The patients, in this patient, we wanted to maintain normal PCO2 and so on, and nobody cared about the pressures. But in 3-4 days, the patient, most of the patients, had pneumothorax. It exploded literally. Then from the barotrauma, with Dreyfus, we recognize the problem of a volutrauma. Maybe the problem is not the pressure, but is the volume. Then we say, okay, maybe it's not the pressure and volume, it's the interface between good and bad part. So it's a sort of atelectrauma, which increase the inflammation. And then here we have the ergotrauma. This word has been proposed by J.J. Marini, which is a trauma which is linked to the all energy that we put in the system per minute. So what is the normal mechanical power? Because mechanical power is necessary. If we do not apply a power to our respiratory system, we die. So we need some mechanical power. Let's see what is the normal mechanical power in a man sitting in front of the sea, drinking a Coke and relaxing. We have to look at the normal mechanical power equation. We have, I'm sorry, because this the translation, but well, let's see. You know the motion equation. The total pressure should be here. At the given moment should be the pressure which is used to distend the lung. And this pressure is nothing else than the tidal volume times the delta pressure. Divide 2 because is a sort of triangle, but this is not important. So this is the elastic pressure. Then we have the pressure which is used to move the gas through the respiratory airways. And the third is the pressure which maintain distended the lung. So here If I have a tidal volume of 6 and respiratory rate of 15 and delta pressure, pleural pressure of 5, so we have a resistance of 10, and this is the ratio of elastance. We have at this is the ideal, excuse me, we have something as well, let's see, 5, 6 joule per minute. If we introduce PEEP, you know, PEEP is quite important because it's the pressure which maintains the lung distended. We have to provide energy to overcome this pressure to move the lung. And so the PEEP, higher PEEP increase substantially the mechanical power. So now we have to consider tidal volume, PEEP, flow. All these are linked to energy load per breath times the respiratory power. We got the respiratory rate. We got the mechanical power. So, what's about the tidal volume? This is all the story. Everybody knows that tidal volume, high tidal volume may be dangerous. What I suggest you to consider tidal volume in the framework of all the lung. You know, with the lung we have the FRC, which is a lung resting without any pressure at end expiration. Then we may have a PEEP. So we add with PEEP, we add a tidal volume, excuse me, a PEEP volume. Then we have the tidal volume. Then we have the physical limits of the lung, which is the total lung capacity, in which the lung is fully distended, all the extracellular max matrix is stretched, and if we have the change in volume divide the FRC, this is called the strain. So let's see, if I have an FRC in a very severe patient with 500, half a liter, my total lung capacity is about 1.5 liters, about 2.5, 3 times the FRC. Then it's quite easy to see that if I overcome at each breath the total lung capacity, the damage may be relevant. Everybody knows what is the classical ARMA study, and we know that higher tidal volume, 12 in this case, was worse than lower tidal volume, 6. Be careful not to go too low with the tidal volume, because that means severe hypoventilation. And of course, the tidal volume per kilo doesn't make great sense, because as an example, let's see here, these are the kilo weight, okay? And this is the total gas volume at 5 of PEEP. And you see that mild, moderate, severe, we don't have any relationship between the gas volume at 5 and the amount of tidal volume per kilo. That means if I have a 70 kilo man, a tidal volume is 6 per kilo, so tidal volume is 420. But the strain is 420 divided 500 if the FRC is very low, or is 420 divided 1,000, or 1,000 and a half, or 2,000 in covered patient. You know that the strain is completely different, so it's a bad substitute of strain in tidal volume per kilo. We should normalize per the gas volume, initial gas volume. And you see here, this is an example Then when we have higher PEEP, and we have overcoming the total lung capacity, the strain is very high. And at least experimentally, we found the VILI, because VILI, the ventilator-induced lung injury, is something that can be studied, I think, only experimentally, because in humans, the manifestation of VILI are the same of the manifestation of normal RDS. So it's quite difficult to distinguish how much is due to the respirator, how much is due to the normal evolution of the disease. Here, experimentally, we found that if the strain is greater than 1.5, which is pretty high, nothing happened to the lung weight. And lung weight, here, the edema in 48 hours experiments were taken as a sign of the lung damage. While if the strain exceeds 1.5, you see the lung weight increase a lot. So there is VILI. So tidal volume, no doubt. And is important also to consider the time. Okay, these are the evolution of these are hours, and look at the CT scan. And you see the first manifestation of tidal volume of the VILI are these little knobs here around the border between pleural and visceral, visceral and lung pleural, because we have the greatest difference in elasticity over there. And you see here increases. At this point, we have some problem with the mechanics. Then we have some problem with gas exchange. PEEP. What's about PEEP? Everybody knows that PEEP is important. And we know since a long time that if we increase PEEP, the weight of the lung increases. Look here, this is a very old study in the 80s, no? Not so much study. And you see the PEEP 0, 5, 10, 15. And you see that increasing PEEP, we have problem. Now has been shown also in humans. Then we exceed 15 of PEEP. This was a study, the Brazilian study, the ART study. You may have definitely an increase in mortality. This is another example, the time increase in the PEEP 0, 5, 10, 15, 0, 5, 10, 15. So, my dear friends, when you touch the knobs of the ventilator and you increase the PEEP, remember that you are inducing a possible, not only possible benefit on gas exchange, but a possible accumulation of water and damage in your patients. This is a study we did experimentally. You can see that the fluid balance, here we had the isomechanical power, the same mechanical power, but provided increase in tidal volume or frequency of PEEP. When the mechanical power, the same mechanical power, but increasing PEEP, there is a tremendous amount of difference in terms of water accumulation in the lung, but overall in all body. So we know also that when we compare higher and lower PEEP, that means 7, 8 versus 12, 13, in case of lower PEEP, we have the possible damage of athalec trauma. With higher PEEP, we have a possible damage of volotrauma. And if we look at the study we did in this range of PEEP, the risk of atelectatic trauma and the risk of volutrauma in the general RDS population are very similar. We cannot distinguish. But if we exceed 15, the PEEP definitely is dangerous. So be careful of PEEP. So we have seen tidal volume, we have seen PEEP. Now, flow, rate, and distribution. I don't want to, these were experiments we did with Proti years ago, and we use a similar strain, but different rate. So in one case, the strain was provided very rapidly. In the other case, it was more smoothly. And of course, if I have a strain very rapidly, the amount of energy is concentrated in lower time. And this was causing some problem compared to the smoother increase of energy. And this is the distribution of mechanical power. You see, here the intracyclic, we did that with Marini. You can see how may be different the distribution of mechanical power in time in a single breath. So even the rate of flow and the flow, of course, are potentially important. So we examined the volume, PEEP, flow, rate of flow. And what's about PEEP? We have a lot of discussion if considering the PEEP part of the mechanical power. If you ask whatever engineer, he tell you yes. Because, to move the lung from this level of volume, I have to provide energy to reach this point, if not the lung deflate. After that, I use this is all the energy, pressure times tidal volume. Remember, what is important is the pressure, the absolute values of pressure, not the change in pressure for the changes in tidal volume. Pressure times the tidal volume is the energy. And then we have another possible cause of damage is the, let's see, the distribution of stress and strain. If I have two parts of the lung, in which one is very elastic, the other one is collapsed or cannot expand anyway, at the interface, I generate a concentration of stress, of pressure, and concentration of strain, which has been shown, theoretically at least, to be quite important. This is the basis also of the atelectatic trauma. And I'll give you here an example. If I have here a unit which is collapsed or consolidated, cannot move, all this lesion, this connection are stretched. When I inflate these units, these regions becomes another possible source of damage. So, mechanical power is the energy per breath per minute. We examined so far which are the components of energy in each tidal volume. But here we have another thing, respiratory rate. And the curious thing, the respiratory rate is usually neglected. If you look also at the ALMA study, using 15 or 25 or 30 respiratory rate is quite equivalent. Now, but try to, if you have a hammer, and try to pick your hand 1 per minute or 30 times per minute. The damage is different. So it's a very common sense apply. All this put it together are the mechanical power. This is an example of how energy is important. The respiratory rate is important. If I take a set of energy per tidal volume, which I know may be a disaster at frequency of 12, 15, if I use 6 of frequency, I don't have any problem. That means, at least in experiments, usually our experiment lasts 48 hours. So this tells you what is the relevance of the frequency. So let me give you another example. Here we have a experimental group, in which we had the same mechanical power, more or less, 20 joules per minute in peaks. But we have a different package. In these patients, in these peaks, the mechanical power was reached mainly for a very high tidal volume, 30 milliliters per kilo, with the PEEP, which is quite normal, 5, and respiratory rate around 10. Okay. Here we have respiratory rate around 40, tidal volume low, 10, and PEEP 6, 7. And here we have higher PEEP. So we have the same mechanical power, the same package, the volume, total volume mechanical power is the same, but each component, its determinants were different. Are the damage different or not? I already told you that when I use this setting, I have more water in the body, not only in the lung. But for what the lung is concerned, we had exactly the same damage in experiment. So the problem is with the mechanical power, which is essential for life, too much or too low. If there is any threshold, well, look here, which is quite interesting. You can see here, lower group, higher group, a series of studies, the high-low study, expert study, love study, the R study, in the lower group and the higher group, compared in the different studies. 6, 6, 6, 6, the tidal volume was similar, respiratory rate was similar, peak pressure was not very different, plateau pressure was a little bit higher here, but not extremely, PEEP, but look at the mechanical power. The mechanical power here was 28, here the mechanical power joule per minute was about 34, and this is the only one in which we found a difference in mortality. So PEEP is extremely important, and the PEEP is a big component of mechanical power. So if we have the mechanical power is too low, we have a series of damage. Insufficient ventilation, PC2 rise, PC decrease, atelectacy, worsening of hypoxemia, and so on. Here, mechanical power too high, extracellular matrix injury, overdistension, decreased cardiac output, ventricular failure. We are studying now the possibility to identify a threshold for mechanical power. Previous study is on the only one in humans was around 18 joules per minute. But we are now studying a concept to identify a sort of mechanical power ratio that means to compare the mechanical power, which is dangerous, with the mechanical power, which is normal, okay? And what we found, a possible threshold that we can tolerate the mechanical power This experimentally works quite well. In the humans, I don't know, but about 4 times normal. So normal means at rest. If I have 4 times the energy, it's still up to 4 times I can tolerate. Greater than 4 times, I have damage. So I think if I had to use the mechanical power in a general entry, this is the way we try to assess the things. A patient comes in, the assessment of the dimension of the baby lung, size, homogeneity, and recruitability, and we save prone position and the same mechanical ventilation. If the mechanical power threshold is overcome, yes or not. If I cannot decrease the mechanical power below a given threshold, I have to use some extracorporeal support. This is a little bit the way we are going. I thank you for the attention.